After we've discussed various decidable theories, we now proceed to look at the arguably most famous undecidable theory, namely Peano arithmetic. So let's fix the language. This is going to be the language of arithmetic. It's going to be a little bit different than the one we had before. The main difference is that we replaced one constant by a unary function symbol s. So this is unary function. And of course, it's intended to be the successor function. We also have plus times as before, and we also include less than. This less than is a binary relation, of course, but it turns out to be an expansion by definition, as we will see from the axioms in a moment. We will also make frequently use of the constant terms. So these are terms representing the natural numbers in a structure, and we can get those by letting the constant term 0 be just the 0 symbol, and then the constant term n plus 1 is the successor of the constant term n. So you can think of this term being 1 plus 1 plus 1 plus 1 plus 1 n plus 1 times. And these constant terms will allow us to talk about, in any structure, here L arithmetic, of a version of the natural numbers. Now we come to the axioms. So we start with a finite group of axioms. They are very simple. They just express basic facts about how the operations work, and of course they are intended to cover or capture basic arithmetic among non-negative integers. So for example, for every x here, the successor of x is not equal to 0. For every x, every y, if x is not 0, then it has a predecessor. And of course here now you see I already slipped back into the old notation. So this should of course be s of y. All right. And then the next one, if two successors of are the same, then the numbers are the same. Addition, here those two next axioms actually say that addition is, so the addition symbol, or the function given by addition, is obtained from the successor operation inductively, right? So if you look at these two axioms together, this is just the recursive definition of addition. And these two axioms tell us that addition has to be related to the successor function in this way. And similarly for multiplication, so P6 and P7 essentially just tell us that multiplication is obtained recursively from addition. So these 7 axioms together actually have a name. They're also called Q, after Robinson's Q. And the important fact here is that this is a finite theory. So there's only finitely many axioms. Now the axiom P8, as I already mentioned before, is just ensuring that less than is an expansion by definition, because we can define less than using the other symbols of the language, right, using this formula here. So in the following, we will denote the theory that we obtain by adding P1 through P8, right? So all of these axioms together, this will be PA0. But since PA0, so P8 is just an expansion by definition, it cannot prove more than Q, so it's really the Q is the core of this. So Q is a finite theory, but it is actually quite weak, as we will see. It just captures some very basic facts about arithmetic. To get full PA, we have to add the induction axiom, which is really not an axiom but a scheme, because we have to add for any formula, right? So for any formula phi, phi, this is an axiom. So let's call this int phi. Right? And if we add these infinitely many axioms of this form, right? For any formula we add one, so there's infinitely many formulas. So we have to add infinitely many formulas. If we add this to Q, we get the theory of Peano arithmetic. So this is not a finite theory anymore. So we have the following relation between the different theories. Clearly Q is a subtheory of PA, but Q, as we saw, is finite and therefore recursively axiomatizable. PA is infinite, but still recursively axiomatizable, because if you can check whether a formula is of this form. So we have a still recursively axiomatizable theory. And of course, both are subtheories of the theory of the natural numbers, because all of those statements hold in the structure of the natural numbers. So that's so in particular, every sentence in PA is a true statement about the natural numbers. So this is infinite, of course. And as we will see, the theory of the natural numbers is not decidable. Now, what do models of Q or PA0 look like? Of course, we always have the standard model of the natural numbers. But as we have already seen as an application of the compactness theorems, there are also non-standard models. And non-standard models are those that have elements that are different from the interpretation of this constant symbol n for every n in n. Models of PA0 can also look quite differently from n. So as an exercise, I encourage you to think, if you can find a model of PA0 or Q such that this doesn't hold. So for all x, the successor of x is different from x. However, there's one important fact that will be actually quite important for us about models of PA0, namely they always contain an isomorphic copy of the natural numbers as an initial segment. So what exactly is an initial segment? It's probably you have already a good idea, but let's look at the formal definition. So to structures, we say n is an end extension of M, and correspondingly M is an initial segment of n, if and only if M is a substructure of n, and for all A in M and B in n, if B is in n below A, then it's already in M in the smaller structure. So there's nothing between the elements of M in the bigger structure n. And the theorem is that if we have a model of PA0, then the mapping that maps the natural number n to the interpretation of the constant symbol n in M, that defines an embedding of the standard model n as an initial segment in this sense here of M. So in other words, n is an initial segment of M. M is an end extension of n. In order to prove this, you have to kind of go through the following steps. And of course, I encourage you to do that. First, you show that addition and multiplication defines a homomorphism of the structure when restricted to the interpretation of the constant symbols. So our mapping that we're interested in, right, namely mapping n to interpretation of m in M, that will be a homomorphism. So how do you prove this? Well, you do it by induction. And now you will say, well, wait, don't we lack induction in PA0? Yes, we lack it in the theory itself, but we still have it in the meta theory. And as you see, we don't show this in the form of for all n or something. So we don't show like for all n or something like that, right? So this is an individual statement, right, about a single instance for two numbers or two constant symbols. Right? And this you can show using induction in the meta theory. So induction on n, where n now is an element on of the natural numbers. So you can think of this as maybe naive induction or induction in the meta theory. Right? And as I said, this is a single statement, right? And then once you have showed this holds for one n, then you move on to the next n, and so on. You don't show a for all statement here. Next, you use the axioms to show that the less than relation is preserved under successor. So for this you use the axioms, and this allows you then also to conclude that this holds correctly between the constant symbols whenever n is less than m. Right. So what you essentially do here is that PA0 can prove some very basic facts about the structure of the constant symbols, right, inside a model, that it behaves more or less like the natural numbers, right, in the way that we want it to behave. And then finally, you can show this here, namely that now we have actually a for all statement here that PA0 can prove, namely that if you're less than a k, then it has to be 0 or k minus 1, so one of those constant symbols. And this is again proved by naive induction on k. And then finally you can conclude that if you have an element of your model and that is not from n, so of course now by n we mean the image of this embedding here, so that is not coming from that, then it is actually true that C is greater than the interpretation of any constant symbol n for any n natural number n. So to sum up, the first two here tell us that this mapping is a homomorphism. So indeed, we can embed the natural numbers here as a substructure. And then these two facts together tell us that this will indeed, this substructure, right, that we get by this embedding here will indeed be an initial segment, or in other words, M is an end extension of